Hello everyone, welcome to MedDevice. This video is the second part on the topic of oxygen hemoglobin dissociation curve. So let's start. So in the first video, what did we discuss? So we had discussed the hemoglobin saturation, the partial pressure, normal OHDC, positive cooperativity, and P50. In this video, we will be looking at the left and right shift, Boers and Haldane effect, changes in the OHDC due to fetal hemoglobin, carbon monoxide poisoning, and myoglobin. So let's quickly review what we have learned in the first video. So we had seen that the normal OHDC is sigmoid in shape, and this sigmoid shape is due to positive cooperativity. What is this? This is a property where binding of one oxygen molecule on hemoglobin increases the affinity of the other oxygen molecules to bind. So if one oxygen molecule will bind to the hemoglobin, it will make it easier for other oxygen molecules to bind as well. We had also discussed that the saturation of hemoglobin depends on the partial pressure of oxygen. So if partial pressure of oxygen is high, the saturation of hemoglobin is also going to be high, and vice versa. What was P50? It is the partial pressure of oxygen when the hemoglobin is 50% saturated. And finally, the hemoglobin is about 97% saturated in the arterial blood and 75% saturated in the venous blood. If you haven't watched my previous video, so I highly recommend that you go and watch that so that you are able to understand this video better. Okay, so let's start with the first subtopic, which is right shift. So here, following the thick red line, you can see that this is the normal OHDC. But the dotted red line shows that the curve has shifted to the right. Now to understand the right and left shifts, it is important to understand why does this happen, where does this happen, and when does this happen. So we will try to answer all of these questions in this video. So let's see why the right shift happens here. So let's go step by step and let's see P50. P50 here will serve as a reference. So let us draw a perpendicular line on the P50 point for the normal OHDC. Now let us compare the partial pressure of oxygen in both of these cases. So what do we see here? We see that before, little pressure was enough for hemoglobin to get 50% saturated, meaning when the partial pressure of 25 was given, 50% of the hemoglobin got saturated. But now, more pressure is required for hemoglobin to get 50% saturated. So now, as you can see from the graph, we have to give about 35 to 40 mmHg of oxygen for the hemoglobin to get 50% saturated. So what does this signify? It tells us that the affinity of oxygen to hemoglobin is decreased. Affinity in a way means love. So the love between oxygen and hemoglobin is decreased. Because oxygen is not readily binding with the hemoglobin, right? You have to give a lot of pressure for the hemoglobin to get saturated. So the love in a way is decreased or affinity is decreased. So decreased affinity means the oxygen is dissociating or unloading from the hemoglobin easily, right? Now where do we want this? Where do we want that the oxygen easily dissociates from the hemoglobin? We want it around the tissues, right? So that the oxygen can be delivered to the tissues. Now, why does the right shift exactly happen? This happens around the tissues for a number of reasons. This happens due to increase in carbon dioxide, H plus ions, temperature, and 2,3-DPG. So all of these are increased around the tissues, and these facilitate the unloading of oxygen from hemoglobin. So again, increase in carbon dioxide, H plus ions, temperature, and 2,3-DPG. So everything here is increasing, but in the question if they mention pH, so remember that pH is decreasing because increased H plus ions leads to decreased pH, right? So don't get confused in that point. Now let's see the opposite or left shift. So here you can see that the dotted line has shifted to the left. Now again let's go step by step and see what exactly is happening here. So again let us see the P50 point and let's draw a perpendicular line for the normal OHDC. And now let's compare. So we can see that before, more pressure was required for hemoglobin to get 50% saturated. But now less pressure is required for hemoglobin to get 50% saturated. So just imagine that we gave a little pressure and a lot of hemoglobin got saturated. So what does this mean? This means that there is a lot of love between hemoglobin and oxygen, or in other words, the affinity is increased. Now, increased affinity means that the oxygen is attaching or loading to the hemoglobin easily. Now, where in the body do we want this? We want this around the lungs, right? So that the oxygen which is coming from the air easily attaches to the hemoglobin and then is delivered to the tissues. Now, this happens when carbon dioxide, H plus ions temperature, and 2,3 DPG are decreased. So, a decrease in them leads to the left shift. So, if these are decreased, oxygen will go and happily bind with the hemoglobin. You can remember it this way. All of these four are like the toxic relatives in a relationship. So, because of some reason, these relatives will come and try to destroy a relationship between two people. Similarly, these four are trying to destroy the relationship between oxygen and hemoglobin. But if you remove these toxic relatives out of the way, the oxygen and hemoglobin are going to live happily ever after. Okay, now let's try to understand what exactly is this 2,3-DPG and how does increasing it cause a right shift. So it is a byproduct of the glycolytic pathway. Now what effect does it have on the hemoglobin? So take this to be the hemoglobin. Here we have two alpha chains and two beta chains. So 2,3-DPG comes and sits in a pocket, and now there are electrostatic interactions between 2,3-DPG and the beta chains. So important to remember, the interactions are between the beta chains and 2,3-DPG, not alpha chains. Now this binding will stabilize the low affinity state of hemoglobin. What does low affinity mean? It means no love, right? So now if no love will be there, the oxygen will be released from the hemoglobin and will go to the tissues. And we also know that if oxygen is released and the affinity is low, what is this going to cause? Correct, it will cause a right shift. So that's why 2,3-DPG causes a right shift. Now, what is Bohr's effect and Haldane effect? So Bohr's effect explains that an increase in the partial pressure of carbon dioxide and H plus ions leads to decreased affinity of oxygen to hemoglobin. This is the same as what we just studied. Haldane effect is exactly opposite. An increase in the oxygen leads to decreased affinity of carbon dioxide and H plus ions to hemoglobin. So just knowing the definitions is enough. Now very important, how does the OHDC look in a fetal hemoglobin? So first of all, we need to know the difference between adult hemoglobin and fetal hemoglobin. So in this adult hemoglobin, as we just saw, you can see two alpha chains and two beta chains. And here we have the fetal hemoglobin, where instead of beta chains, we have gamma chains. Now I'll ask you a question. If there are no beta chains, is the 2,3-DPG going to bind? No, it is not going to be able to bind. So what does this mean? This means that the oxygen can attach to the hemoglobin, or in other words, the affinity is increased. So since the toxic relative 2,3-DPG is not there, the love will again increase. And if affinity is increasing, the curve shifts to the left. Now, is this beneficial or not? So if the fetal hemoglobin has high affinity, it can extract oxygen from the mother's blood. And this is exactly what we want for the growing fetus. Now, what about carbon monoxide poisoning? What happens here? So, carbon monoxide has about 250 times more affinity to hemoglobin than oxygen. So, it will come and bind to the oxygen binding sites very tightly and will not let go. And if it will do so, there will be some sites remaining in the hemoglobin where nothing will be sitting, and there the affinity of oxygen is going to increase. Let's try to understand this with an animation. So imagine in the first case you have only oxygen and the partial pressure is high. So all the binding sites are going to be occupied by oxygen. But in the second case, let's imagine that you have some oxygen but also carbon monoxide. So carbon monoxide is going to come and bind to the hemoglobin, and it is going to make very strong bonds. So now you can see that there is only one space remaining in the hemoglobin. This site is going to have very high affinity for oxygen. So to summarize, carbon monoxide is causing two things. The total number of oxygen binding sites is decreasing because instead of oxygen, carbon monoxide is coming and sitting there. Because of this, it will lead to a decrease in the oxygen in blood. But the remaining sites are going to have an increase in the affinity for oxygen. And what have we just learned? If the affinity or love is increased, the curve is going to shift to the left. So let's see what we can see in this graph. So first of all, if you will look at the white arrow, you can see that the curve is shifted to the left. What does the yellow arrow represent? It shows us decreased saturation, right? Why decreased saturation? Because instead of oxygen, carbon monoxide is there, right? So oxygen is not able to bind to the hemoglobin, and so the saturation is decreased. Now finally, coming to myoglobin, what happens here? So here again we have the adult hemoglobin and here we have the myoglobin. So let's see what are the exact differences between them. So hemoglobin is tetrameric, meaning it has 4 chains, 2 alpha chains and 2 beta chains. It also has 4 heme and cooperative binding is seen here. Finally, the OHDC here is sigmoid in shape. What about myoglobin? Here the myoglobin is monomeric, meaning it has a single polypeptide chain. It has one heme. Now it is very logical. If I ask you, will cooperative binding be seen here or not, what will be your answer? So there will be no cooperative binding seen here. Why? Because binding of one oxygen molecule makes it easier for other oxygen molecules to bind, right? But here only one oxygen will be able to bind because it has only one site. So there is no cooperative binding seen here. And hyperbolic dissociation curve is seen. Let's see what that looks like. Now I'll ask you two questions and try to answer. A sudden rise in saturation is seen here. What is the reason? So the reason is that there is only one binding site. So if one oxygen will come and bind to the hemoglobin, it will immediately get 100% saturated. That's why there is such a sudden rise. Second question, why is the curve shifted to the left here? The answer is that the single binding site, which is here, has very high affinity for oxygen. And as we know, if the affinity or love is high, the curve is shifted to the left. That's it for this video. If you have any doubts, so please leave them in the comments or you can message me on Instagram anytime. The link to my Instagram is in the description. Thank you.